This is going to be a talk about Empire, which is an internal platform as a service that we built at the company that I work for, and it's based on Docker and AWS services. Before I start, though, can I just have a quick show of hands? Who's using Docker in production right now? Oh, it's actually quite a few. What about ECS in production? Yeah, a couple. Cool. Oh. So I'm going to start a little bit of background about why we decided to build a platform as a service, and our path that kind of led us to build Empire, and how we're ultimately leveraging ECS, or Amazon EC2 container service, as the backend for Empire. But first, a little bit about myself. My name is Eric Holmes. I'm an infrastructure engineer at Remind, and I like building things for other developers. I work mostly with Go these days, but my background, I did a lot with Ruby. I open source a lot of crazy ideas on my GitHub, which is at @ejholmes. So I work for this company called Remind, and we build a product for teachers that makes it easy for them to communicate with students and parents. We have 3 major features. One of those is real-time chat. The other major feature that we have is announcements, which allow teachers to send a fan-out message to all of their class, like if they have homework tomorrow. And then we also support files, attaching files to both chats and announcements. So right now we have about 25 million users. During the back-to-school period, which is basically next week, which is when all the kids come back to school, we add about 350,000 new users to our product per day. And we send about 5 million messages per day. And we do all this right now with about 50 employees, about 30 of which are engineers. So we're growing really fast. So a little background about the historical architecture of our application. So the product started back in 2011. We had a very kind of similar feature set to what we have today. This is sort of after we discovered what the product really should be. But the technical architecture was vastly different from how we are today. We didn't have a lot of users. We didn't have a lot of scale. So we started as, like a lot of startups, we started as a monolithic Ruby application, Rails application. And this single application served our API for our iOS and Android clients. It served our web dashboard. It handled all of the message delivery that we did through Sidekick queues. And it also handled class widgets, which is this little feature that we have for embedding a message stream on users' websites. So this architecture worked out really well initially. We didn't have a lot of users, and iterating on a single monolithic application was really easy and really fast. But we started to grow really quickly just by word of mouth. And during these back-to-school periods, we're getting a little scary because we were adding so many users per day and getting so many requests per day. So I wanted to show a graph here what our traffic actually looks like during back-to-school, but I was told that I can't actually share the actual graph, but it kind of looks like this. So it's very steep. It's actually steeper. I should kind of like rotate this a little bit. And it goes just really high, then it kind of drops off as the school year goes on. But back to school is just this huge spike in traffic and spike in new users and message delivery. So during this back to school period, with our message delivery still living inside of our single Rails code base, we started to run into a lot of problems. One of those being that our Sidekick queues were constantly backed up, and it was difficult for us to really scale this out horizontally. Because it was really tightly coupled with the rest of the code base. And we were storing a record of all the deliveries that we made to SMS devices or applications. And this was a lot of deliveries. And we were storing all this inside of our single Postgres database that stored other information about users and groups. And we realized that we were either going to have to shard this or we were going to have to split it out into a separate service. So we opted for splitting out into a separate service, which I think was the right decision. And we kind of continued this over the past 2 years as we've grown. And now we have approximately 40 to 50 or so production services. Up until very recently, we were running all of these services on Heroku. And we started using them back in 2011 because they allowed us to build the product very quickly and not focus on building infrastructure to support it, like how we would deploy things. Heroku was a really good decision, I think, for us initially, because we didn't have to hire a dedicated ops team, and we just focused on building the product. But it became clear to us pretty recently that there's a lot of constraints that Heroku provides that kind of start to break down for a microservices or a service-oriented architecture. One of those being that all of our internal services needed to be exposed publicly because there's no equivalent to like a VPC inside of Heroku's platform. One of the other things was that our databases need to be opened up to internet traffic, and this is generally not a good idea. And we didn't have a lot of visibility into CPU, memory, and network performance of the hosts. So if a host is dropping packets, we actually wouldn't even know. And we didn't have any control over the routing layer. So if we wanted to do custom request IDs or have authentication moved into a middleware layer, that was very difficult to do. So about 7 months ago, we kind of took a step back and asked ourselves, well, what do we really want in internal platform as a service? So one of those things was that we were already using a lot of AWS services like DynamoDB and Redshift, and kind of through proxy via Heroku. And the other thing is that Heroku does a really good job of making operations very simple. So there's a lot of operational simplicity about Heroku. Things like deploying, configuring, it's just a couple of CLI commands away. So this is something that we really wanted to maintain. And thanks to Heroku, we were kind of sold on the constraints of the 12-factor application model. If you're not familiar with 12-factor apps, it's kind of like a philosophy or a set of best practices for how you should run stateless service applications or services. It's like configuring via environment variables and making processes disposable and scaling out horizontally. We also wanted to maintain shared patterns for deployment. So we wanted all of our services to get deployed exactly the same way, which is how we were doing it on Heroku. And this is really good because it lowers the barrier of entry for somebody getting something into production. You don't want to get into a scenario where somebody has to make a change to a service, but they have no idea how it gets deployed. We wanted to maintain very fast build and release iteration cycles. So since we were previously on Heroku, we didn't want to have a dedicated ops team. We were kind of operating under a no-ops philosophy prior to being on Heroku. And we didn't want to end up in a world where we would have to talk to a big ops team to get something new into production. So we were also getting really concerned about the size of our surface area. Like I said before, all of these internal services need to be exposed publicly on the internet. And we wanted to decrease our surface area and only expose what actually needed to be public. And then the rest of that, we wanted to live inside of a VPC. So all of our internal services would only be accessible within our internal VPC. And probably most importantly, whatever we built for this, we needed to be robust and resilient to failure. We're operating a fairly large-scale production system, and downtime is like a very serious thing for us. So we needed something that wasn't going to cause downtime. And ideally, we wanted to use containers as a unit of deployment. And I'll talk about some more reasons about that, why in the next slide. But we're actually kind of technically already using containers on Heroku. They use a containerized technology. But we wanted to take a next step and possibly use Docker if we could. So why containers? The reason kind of boils down to speed and cost. So containers, they can be built really fast. There's some caveats to this. There's some bugs in Docker that make that kind of hard to do in a build system. But for the most part, you can build a container and push it up in 30 seconds to a minute, which makes it very easy to make a change and then deploy it to production. They let us isolate dependencies as a portable, really easy to distribute package. I think probably the best way to think about containers is they're kind of just like statically linked binaries. If you're familiar with Go builds statically linked binaries and they're very portable. Containers are kind of just the next step. You can isolate dependencies and they're portable across Windows and Linux systems if you're running Vagrant or something like that. They also let us build better development environments and have more dev prod parity. So the same images that we're building in our build system can be run on a developer's laptop if they want to debug something. Or if they even want to set up the entire service locally on their laptop, they can just pull a bunch of Docker images and connect them together. They limit the number of moving parts, and this just kind of boils down to immutability in infrastructure, which I think is a really good idea. The thing, if we build a Docker image now and deploy it, if we take that image again in 6 months from now and deploy it again, there really shouldn't be any change. And then containers, they allow us to use resources more efficiently. So cost was an issue for us, and we can run, on average, we've been running about 10 to 20 containers on a single host, and that really allows us to bring in our costs. So we decided that we wanted an internal PaaS, and it turns out we're probably not the first company to want something like this, or to try to build something like this. So one of the most well-known companies that sort of expose the benefits of microservice architecture is Netflix, and they have something called Asgard, and they use a lot of AWS services as well. And they bake AMIs. I think they might do something a little bit differently now, but the last time I read about this is they bake AMIs and they use that as a unit of deployment. So it's kind of similar to like building Docker containers, just at a bigger scale, and it's a lot slower, unfortunately. So Docker containers allow us to build things a lot faster. SoundCloud is another company that kind of built an internal platform as a service. They call it Bazooka. They're not using containers, but it's kind of similar to what we wanted, where it was something akin to Heroku that provided ease of operation. And pretty much every other company inside of our investors' portfolio is trying to do something kind of similar to this. So ideally, we didn't want to build something if we didn't have to. We spent a lot of time researching open source PaaSes, and a couple of them looked pretty promising at the time. Two of those were Flynn and Deus. So for a couple of reasons, we decided that neither of these really fit our requirements. Probably the biggest reason for that was that we weren't actually aware of any companies at our scale that were using either of these in production. And pretty much every component that each one of these were using had some kind of alpha or don't use this in production yet statement on it, which is a little scary. So we wanted to ideally use a lot of stable components to build something on top of. So Empire was born. At the time, it was about 6 months ago, and it was just an internal unnamed project. Initially, we started off building on top of CoreOS using Fleet as a scheduler. So Fleet is basically ties etcd together, which is a key value store for clusters. Basically a distributed system D, so you could schedule jobs onto a cluster of machines. We had a custom routing layer that was configured via confd and etcd. So whenever a container would start up, we had something called registrator that would register this key into etcd, and then it would update the nginx configuration so that it knew where to connect to the service or where to connect to the Docker container. And then we were still using Docker at the time. We initially started out by building it as implementing a subset of the Heroku platform API. So we were already really comfortable with using Heroku's tools, and turns out, APIs are interfaces, so you can swap out implementation details, and we can just use the Heroku CLI to do most of what we want to do. This all worked out really well initially until we kind of started testing failure modes. So we discovered a lot of bugs in Fleet that made us just very wary of actually putting this in production. And it became really clear to us that we needed just a more intelligent scheduler. Fleet was very kind of dumb in how it would schedule tasks onto hosts, and it didn't manage desired state well. So if a container went down, it wouldn't actually bring a new one up. That might change now, and I actually think Fleet is actually deprecated in favor of something else. And then in our experience using etcd for managing cluster state and all the machines inside of our cluster, etcd was fragile, and I think a lot of the things in this space are kind of fragile, and it's not something that you really want to run because it's a pain to run and it's a pain to monitor, and it's a very hard problem to solve. And this was back when etcd was not at a stable release. It is now, but doesn't make it really any easier to run, I think. So we weren't really feeling like we were getting the resilience and the stability that we were trying to achieve. And ultimately, we didn't really want to run our own clustering software. So we wanted to, if we could, take a service that could cluster all of our machines together and use that. So, and overall, we were just feeling kind of very frustrated about trying to piece together all these new and just unstable technologies. So around the same time, conveniently, ECS went generally available, and we started looking into this to serve as our scheduling backend for the platform. So what is ECS? I'll kind of breeze through this a little bit, because Chad already talked about it. So I would say in summary, the best way to describe ECS to people is that it's really the easiest way to just run Docker containers on a cluster of machines. And more specifically, it basically pools hosts together as a single resource. And then it provides a set of APIs to place tasks onto a container instance that has available resources. So one of the great things is that it supports the concept of services for scaling tasks out horizontally. And it integrates, this is one of the greatest features, I think, is that it integrates with ELB for connection draining, zero downtime deployments, and health checks that will remove unhealthy containers. So this is really important for us too, because in the previous implementation, we hadn't actually solved zero downtime at all, which is something that we really needed to put something like this into production. ECS is made of a few different components. One of those being the container instance, which is essentially just an EC2 instance running an ECS agent and Docker. So the ECS agent is, it actually runs as a Docker container. You can run it outside of Docker if you want to, but it's usually easiest just to run it as a Docker container. And it's the piece that accepts jobs from a scheduler from the ECS service and runs them using the local Docker daemon, and then it manages the lifecycle of that. So if the container drops, it'll notify ECS, and ECS will reschedule it onto a new host. And then the ECS scheduler is the piece that intelligently places containers onto hosts with available CPU and memory. So then ECS defines a couple of different resources and APIs for interacting with them. One of those being task definitions, which I think you can kind of just think of them as templates for running containers. So you can specify the image, some environment variables that you want to run, and then you can use a service to take this task definition, link it together with a number of desired instances of it, and the service will manage those and make sure that the desired state is kept the entire time. Then tasks are just a unit of work inside of ECS's terminology. One of the great things about ECS is it provides just a raw API for running tasks, which Chad demonstrated for the batch processing. And I think Coursera will too. Then clusters in ECS are they just represent a logical pool of instances that you can schedule tasks into. We tried ECS for quite a while. And just to try it out, we prototyped a backend inside of Empire, and we felt like it would be a really good replacement for Fleet and etcd. So the reason for that is that it provided just a set of solid primitives that could serve as our scheduling backend. So ECS has a GUI, but it also has, just like all AWS services, like a really good API behind it. And probably most importantly for us is that it was a managed service. So all the clustering that we were doing previously that we had to run ourselves, we just didn't have to do anymore. And it's something that we didn't have to monitor either. So if our cluster went down, we were less concerned about having to run that piece of software. And then the failure modes that we tested, they behaved like we would expect them to for something like this. So we can bring up a cluster of hosts and then just kill them all and then let them come back up, and our entire service would be healthy again in a matter of a couple minutes, as long as it takes for the EC2 host to come up. Things like killing container, like if you log into a machine and you kill the Docker container, ECS will spin up a new healthy one. With the ELB integration, if you have health checks to a container, if the container becomes unhealthy, ELB and ECS will bring up a new container, then kill the old one, and register it with the ELB. And then this also meant that because of the ELB integration, we can get rid of our custom routing stack entirely, and we can just do service discovery via standard DNS to the ELBs. So every single service that we bring up inside of our Empire environment that has a web process attached to it, we attach an ELB, and then we just give it a DNS record inside of our internal hosted zone. So if we have like an API service, it'll be available at HTTP/API. And this is really good because if you change environments, so we have a production and a staging environment, it's always available at the exact same location, so service discovery. And this is really good compared to other service discovery methods. Like one of the more popular ones that's talked about recently is like SRV records. But that requires that you change a lot about how you talk to services. And one of the benefits of putting a load balancer in front of it, and especially ELBs, is that we get CloudWatch metrics. It's a single binary, so it's really easy to run. We run Empire just inside of a Docker container, and its only external dependency is Postgres and the AWS, the Amazon APIs. So it provides an API and a CLI to create apps, deploy Docker images, update configuration, run one-off tasks. And it also supports the concept of proc files, which if anybody's used Heroku, allows you to specify like a web process, a worker process, or any other process that makes up your single service. The question that I always get asked is really like, is it ready for production? So we've been actually running about 15 or so production services for the past month and a half inside of ECS managed via Empire. And so far, it's been amazing. ECS has been really stable in our experience. So we've been really happy with it. And one of the important things to remember is that Empire itself, it doesn't manage, it doesn't watch anything or try to alter state. So it takes a very like hands-off approach once you've deployed an application, and then from there it's all AWS services. So it's ELBs, ECS, EC2, just these existing stable technologies. And one of the great things is we've seen huge performance improvements moving off of Heroku and directly onto EC2.
All right, so I'm going to go ahead and jump into the demo now. I'm going to start with a simple example first, then I'll show you how you can use Empire's application model to deploy more advanced architectures. So before using Empire, you need to provision an instance. We have a really simple CloudFormation stack that you can use to build an Empire environment. This will create all the necessary AWS resources and return an HTTP endpoint for the Empire API URL. So all you have to do is go to the Empire repo and click Launch Stack. And this is going to bring up the CloudFormation UI. So you'll just click Next. And it'll present you with some options. You can actually leave most of these blank. And when you click Next, it'll ask you a couple more things. But once you do that, it'll take about 10 minutes or so to create an Empire environment. For the sake of the demo, I've already done this beforehand because it'll take a little while. But I can go ahead and jump into the next section. So once we have Empire running, one of the great things about Empire is it makes it really easy to deploy Docker images. So you can deploy any Docker image from the registry. So for example, I can really easily deploy the Nginx image to an Empire environment. So before we actually do anything, we'll have to first set the Empire API URL so it knows where to connect to the Empire API. So I've already gone ahead and done that. And then we'll need to log in. And with the example stack, the username is fake, and there's no password, so we can just log in. So the next thing we can do is deploy, for example, just the standard Nginx. So we can easily deploy the official Nginx image to our Empire environment. That pulled the Nginx image from the registry. It created the ECS service for the web process, and it attached an internal ELB to this ECS service. By default, inside of Empire, all services are considered internal, and they're only accessible within the VPC. It's a lot more interesting if we can actually interact with this service from the internet. Since this is private, we can't do that right now. Empire supports making a service public by adding a domain to the app. I have a sample app that we can deploy called Inspector. So we can go ahead and deploy that publicly. The first thing we'll need to do is create it first. And then we're going to add a domain to it. And then we can just deploy it. And you can even specify tags just like you can when you Docker pull. So there we go. After just a couple of minutes, the ELB will be available, and then we can actually just curl this. So let me just show you the URL for the inspector first. So this is the ELB for our inspector application. And then we can, oops, sorry, I already deployed it. And then we can go ahead and curl this. Cool. So inspector just takes the HTTP request and then returns it as the response. So we can see this is actually working, and we're deploying this application inside of our own Empire environment backed by ECS and all these AWS services. So we can actually show what's running. So right now we have one web process running. And we can go ahead and scale this. Just like Heroku, we can scale individual processes. So we can scale web up to, say, 3 processes. You can even specify CPU and memory constraints when you scale. So this is a Go application, and it doesn't need a lot of RAM. So we can actually scale this to maybe 10 megabytes of RAM. 256, so this is 256 CPU shares out of 1024, just a relative weight. And we'll scale it to 10 megabytes of RAM. And then just to trigger this, we'll have to trigger a deploy again. So after a minute or two, we'll see the new processes running. This takes a little while just because it's doing a rolling restart of all the processes. So we still see there's one web process, but after just a couple of minutes, you'll see there'll be 3 processes here. So we can also set environment variables. And we can list environment. And every time we deploy or change configuration, we'll see a new release. So we have 4 releases. And one of the greatest things about Empire is it actually allows for one-off processes. So if you have migrations that you need to run, like if you're using a Rails console or Python, you can do that with emp run. So for example, we can just run bash inside of a container. And this will actually connect our terminal to this running instance. So we can also use Empire to deploy more advanced architectures. This is kind of a trivial example. So at Remind, we only expose a single Empire application publicly, and this serves as our API gateway. This application is Nginx and OpenResty, and it routes to all of our internal services and applications, like our public API, our web client, and our event service. I have a GitHub repo that shows a stripped-down version of this architecture, and it's available at ejholmes/Empire demo. And I've already gone ahead and cloned that, so we're inside that repo right now. We can bring this up really easily with Docker Compose. And this is just going to bring it up locally. All right, so once we have it up, we can go ahead and open this in a browser. Okay, and this is just a really simple application, to-do application. We can create to-dos, do the laundry, take out the trash. Okay, so when we actually deploy this to production, The architecture that we're kind of going for is something like this, where we have a public internet-facing ELB that is backed by our router, our Nginx router, and this is gonna have reverse proxy to our web application, which is a Ruby application, and our Ruby application is going to consume an internal Go API. So this internal API is not exposed anywhere outside of the VPC. So we can deploy this really easily to Empire by just doing a couple of commands, and I'll show you what those commands are. So I have just a little script that will show us what we need to do. So the first thing we'll do is we'll create the router application, and then we'll add a domain to it. So adding the domain makes it public again. And then for each one of these applications, we're going to build a Docker image. We're going to push it to the Docker registry. And then we're going to deploy that image to our Empire environment. So let me go ahead and do this, and I'll just comment these out because I already did this step beforehand. All right, so we can see that it's starting by building the Nginx image. This is our router application. And right now it's pushing that to the Docker registry. All right, so that one was pushed, and then it also deployed here. So we can see that it created a new release for the router. And now it looks like it's building our API. All right, and it deployed our API, created a new release for it. And now we're building and pushing our Ruby web application. Okay, cool. So we deployed all three images to our Empire environment. So now we can actually see that this is actually running inside of Amazon. So we can do the same thing. Take out the trash. Do the laundry. And we can inspect the processes that are running. So let's take a look at the router app. So we have one web process running for the router, one for web, and one for API. We can also really easily just make changes to our code, rebuild the Docker image, and deploy it to Empire. So if I change web, let's change one of these views, and we'll just change this to say, hello, world. And we'll rebuild this image. Push that new image to the Docker registry. Take just a minute or two. All right, and then we'll deploy this new image. What? Oh. Cool, and now it's deployed. Let's take a look at what we're running. Let's see, I'm just gonna go ahead and kill this. I might need to scale out this cluster. It looks like this one didn't start up yet. So this will just take a minute or two for the new release to get deployed. In the meantime, I can go ahead and show you one of the cool things with emp-run is you can actually do something like curl our internal API. So one of the annoyances if you're running internal services is that they're hard to debug, but it makes it really easy having something like emp-run to basically get access into the VPC. So we can, from the router application, we can just curl our internal API. And we can see that we don't have any to-dos right now. Let's see if our web processes have started up for web. Not yet. Okay, there we go. So now we're running the new release of web. We can open the router application again. Oh. Open router ELB. All right, and we can see that we're running the new version. So that concludes the demo.
You can reach out to me. My GitHub, again, is at EJ Holmes. Twitter is at Vesserin. And again, the Empire repo is remind11/Empire. And the demo is ejholmes/Empire demo. And I've talked about 12-factor apps a little bit. So if you want to get more familiarized with 12-factor, it's 12factor.net.